Hi, everybody. Thank you very much for coming back from tours or waking yourselves up from having walked up a mountainside this morning or whatever it is. But much appreciated. And those of you who are watching in your TV screens while you're kind of half snoozing, welcome and thank you as well. And those who might watch it tonight as they're packing their cases, thank you. Before I kind of start any more today, what I want to do is particularly thank the technical team up there. They've done some wonders today, but during the whole week they've been super. And all the speakers really rely on them and their capabilities. So a big thank you for them. Thanks. And to you guys for all coming. So today, I thought you'd probably be volcanoed out. Although, how could you ever be volcanoed out? Well, Jaime's just fantastic, isn't it? You just and the kind of awesome power of volcanoes is so obvious and clear when you see the size of those big lava flows, and you read that there's a house that's 30 meters below the surface of this, and that was 30 years ago. So it makes you realize something of the awesome power of these volcanoes and the slightly different character of the eruptions that occurred here. But that's an aside. What I want to do tonight or today is switch completely. All right, I thought you'd be volcanoed out, so something completely different. And we're going to talk about fossils, the history of life a little bit, and mass extinctions. We'll finish off by talking about mass extinctions. Okay. So switching away from looking at that image of the Atlantic, and with Iceland up in the northern part of there, in the central part of the mid-Atlantic ridge, into thinking about fossils and what they are, how they evolved, what they can tell us about geological time and environments, and then what were the causes of some of these mass extinctions, and where might the next one be? All right. So we'll talk about what are fossils, how do they form, how they help us to understand geological time and ancient environments, and then we'll finish by talking about mass extinctions. I always kind of start with this, and I'll come back to the image again later about geological time. So the Earth's about 4.6 billion years old. Okay, that's when it started really seriously forming. So that's there on the bottom left hand of that image there. And if you come right across to here, it's really only in the bit that's called the Phanerozoic down here, that animals with hard parts existed. Prior to that point, pretty much most of the animals, 99% of them had soft parts. They were very rarely preserved. We're only beginning to understand them these days as we do a lot more understanding of bacteria and things like that in ancient rocks. So animals with hard parts, 450, 500 million years ago. Man, if we think of this as a 24-hour clock, we come in the last minute of the day, okay? So that's how our fleeting impact on here is seen. And the picture I show on the right-hand one is from the British Geological Survey. And I always like it as a nice picture because it kind of starts at the Precambrian. So the Precambrian is everything from 500 to 4.5 billion years. And then it talks a little bit about all of the different organisms that evolved with time until we get to the top, where man is right at the very top in what's called the Neogene today. So it talks about the different periods of geological time and reflects how animals, plants have evolved over that time, and that's what we're going to talk about in the first part of this chat. Before we go any further, just a bit about paleontology. So paleontology is the study of fossils, and the father of paleontology is Charles Darwin. He was part of that cadre of 17th and 18th century geologists who kind of were the foundation of the science as it is today. As I said in my very first talk, geology is a relatively new science in terms of people's understanding. So Charles Darwin was the man who drove it. Fantastic observations of fossils, his theory of evolution, survival of the fittest, or origin of species are just foundations of everything that's gone on since then. There are some major changes that are going on at the moment, but nothing is still fundamentally challenging that underpinning theory in that way. I put the other one at the bottom. Have any of you seen a film called Ammonite that's been out since it came out? Oh, there we have. I've got somebody who's actually seen it. It came out in spring. So I put there just to reflect that it wasn't just a man's world. Mary Anning worked a lot with Charles Darwin, side by side with him. Never, ever, until recently, is getting the credit that she had. She was one of the first English paleontologists. She worked in the south coast in Dorset, and she was the one who found the first ichthyosaur, which is that this swimming reptile that sits in the bottom picture down there. Stephen Jay Gould, who's a kind of a famous geologist and general scientist, he said he thought Mary Anning is probably the most important unsung or inadequately sung collecting force in the history of paleontology. She spent much of her life collecting fossils, very carefully putting them together, and so she's now just beginning to get the credit. The film Ammonite, as always with movies, it kind of bends life as it really happened, but Kate Winslet stars in it anyway. So if you get a chance to watch it, look at it just for the geology. Don't necessarily think of the story. It isn't all necessarily that true. But everything's underpinned by this. This is where it all started. Now, when we're talking about fossils, and this is what we mean by them, it's any remains of an ancient organism. So it's the trace of the activity as much as the parts themselves. So the trace of the activity, you look at the images I've got along here. The ones on the right-hand side are what we call trace fossils. They're traces of organisms. On the top right, these are dinosaur eggs from China, a very famous locality in China where lots of dinosaur eggs have been found. The middle one shows these tracks, and these tracks are formed in submarine environments, in relatively shallow water, and they're just like kind of fossil wood lice, and we'll come back to that. They're formed by trilobites. But we can look at those tracks and understand something of the ecology of the environment that these formed in by taking the idea that if we look at modern organisms and the organisms that form these tracks today, probably the ones back in the ancient past will be the same kinds of things. And then bottom right here, and I'll be coming back to it later, that's a bit of dinosaur poo. It's coprolite, we call it. We'll come back to dinosaur poo. I've got a slide with some dinosaur poo on later. So those are trace fossils, but they're just as important. They tell us a lot about the ecology of the environment. We can use them to understand also a lot about the animals themselves. With dinosaur footprints, we can understand how they walked, what kind of gait they had, how much weight they were putting onto their back legs versus front legs, etc. So it really does, they're really powerful tools in our toolkit of understanding how fossils lived. And then in addition, there's the more traditional fossils, the ones that we've got in the middle pictures there. On the left-hand side, there's a trilobite called Dalmanites. Don't worry, I'm not going to test you with names. Graptolite in the middle, and an ant preserved in amber. That's probably come from the Baltic area and is relatively recent in geological speaking. But these could be bones of organisms, a lot of the kind of bones of dinosaurs, pieces of shells or complete shells, or bits of protein-based skeletons. And the graptolite in the middle is a protein-based skeleton. You just see them as imprints on there. They're about rocks of about 450 million years old. And each of these funny little kind of serrated bits in there is actually where a little worm lived. They're only about this big maximum, so they're tiny things. And a little worm lived in it, so it's a colonial organism from about 450 million years ago. There aren't any real graptolites that we can see around today, so we have to kind of deduce how they lived. So those are what fossils. It comes from the Latin, means something dug up. Okay, so it's everything that's come from the organism, that's a part of it or a trace it left behind. And the conditions that favour kind of animals being preserved as potential fossils are not easy. Okay, and so really, when we're looking at fossils and collecting them in rocks and we're seeing them, they probably only represent a very small percentage of what the total biotic or organic community was at the time. Because what you need is pretty rapid burial of the rock. So once something's died, like the dinosaur up on the top left-hand image there, it's died, it will fall to the sea floor or to the lake floor or wherever it is, or even on a river. It needs to be tranquil conditions. If it's high energy conditions, the whole thing's going to kind of rot, and all the bones and everything else that will break up and be dispersed. You know, those of you who, I'm sure many of you have been kind of walking on these pristine, beautiful white sands when you're in the Caribbean. When you look under a microscope at those sands, each of those grains are almost invariably broken bits of shell. So, you know, much of that is because these animals have been living in quite active environments and are just broken up. So we want to bury them quickly, tranquil conditions, as much as possible, have no scavengers in the kind of shallow surface and deeper in the subsurface as we bury them. So there's nothing to kind of eat them, no bacteria, no organisms like that will eat them. And then compress them and flatten them, make sure there's no oxygen, so there's a deoxygenated environment. And so if you've got all of those conditions, then the chances are you could preserve a complete skeleton like that of a dinosaur. But you've got to honor all those, and it makes it difficult. So you can recognize that all the fossils we see is only a percentage of the total that we would see totally. And when we seek fossils and collect them, we have two types of assemblages. We have what we call life assemblages, which are those ones that are still in or just about in their living position today. Okay? Or we can have a death assemblage where they've been washed around, brought in maybe by storms. You'll often find them in piles of different shells. All of them are useful in their own way. Life assemblages are rare, relatively speaking. And so often we have to do is put the death assemblages and reconstruct what the life assemblages would have been from the death stuff. Okay? So that's what we've got. I've put a couple of images of kind of life and death assemblages here. This is a great one. If you ever go on the Viking cruise into the Baltic and you go to, I think they're starting to go back to Gotland, or you live in Shropshire area of the UK, these rocks come out there. They're about 420 million years old. It's a Silurian sea. And it's a shallow sea, just like a coral sea today. So the UK and Scandinavia were in a kind of coral environment in those days. Silurians are kind of a part of geological time. So geological time is broken into a series of stages or ages. The Silurian's one of them. All right? It's one of the first things you learn when you're a geologist: Cambrian, Ordovician, Silurian, Devonian, Carbon, and it goes on and on, right the way to today. All right, so it's about 420 years old, a Silurian shallow sea. So if you were around in those days, you could snorkel in there, and it'd be like snorkeling over a reef. And these are what we see. The outcrops are there in the top left-hand image, and the bit I want you to kind of focus on is right in the middle, that lumpy bit in the middle. It's probably about this big, that lumpy bit. And when you look at that lumpy bit, it's formed of all these kind of organisms. These are ancestral coral types that sit on the right-hand side. Is another funny name, stromatoporoid. I'm not going to test you on that one either. But they were ancestral corals. They weren't the same as corals, but they lived in the same kind of environment as corals. So by understanding modern coral reefs and seeing these at outcrop, we can recreate these patch reefs that existed 420 million years ago, which is that image on the bottom left-hand side. So looking at all the fossils that we occur in there, these different kinds of fossils, these are called crinoids or sea lilies, and they gave you those kind of floral kind of images there. The corals themselves, or the proto-corals, are those kind of brainy type features in there. And then within there you get lots and lots of other shells. So don't often get these. These are fantastic examples of an in situ life assemblage. Most of the things we get are like this. It's just piles of shells, whether it's piles of crinoids up in the top right hand, or ammonites down here, or a variety of different ancient mollusks in there, or back to our graptolites that I showed you before. But you can see they're all together, they're all hashed together. They've probably been brought in by a storm or some kind of activity like that. Or they've died and they've just gradually settled into onto the sea or the lake floor. So the top left-hand image is the ancestral bird Archaeopteryx, and it's a famous image from the Sollenhofen limestone in Germany, which is a lacustrine limestone, very quiet conditions. Literally the bird died on the sea and it just settled gently and gradually into what was an anoxic and smelly fetid lake bottom. and preserved Archaeopteryx with all of the, you can see the ancestral feathers and everything else like that. A very, very famous, a world famous fossil. But these are death assemblages, and we have to use them and put them together by understanding modern environments. So what we do is we have to do tough things, as I said in my very first talk when we were talking about sedimentary rocks, because these are sedimentary rocks. You have to go and force yourself to go and snorkel on coral reefs, really go places like that. It's tough. It really is tough. So that you can understand how these ancestral corals, so these are about 300 to 400 million year old coral types. So they're not the same as modern corals. They're a different kind of coral, but they lived in the same kind of environments. And how we can use those to understand how these limestones on the left-hand side were forming and how they formed as reefs. So the top left-hand picture is from Canada, from about 400 million year old rocks in Canada. And you can see the lumpy bit in the middle of the image, which is this bit up here. All right, up there. That's a Devonian reef. And it's formed of corals or ancestral corals that look like that. The one on the bottom left is one from the central part of the UK, from Derbyshire. And again, you can see a little inclined lumpy bit there, which is another small patch reef of its age, of its Carboniferous age. Okay? So it's the present, as I said in the very first talk, the present is the key to the past. Understanding modern environments, modern organisms, and then using them to understand how ancient organisms, even though they're not the same forms, but look the same way, existed. So that's how we use them to get ancient environments. Paleontology now has really transformed over the last 10 or 15 years. So when I was taught particularly vertebrate paleontology, it was as dry as dust. It was just a story of bones. Now with modern biochemical techniques and geochemical techniques, with visualization capability, with computer-assisted design, applying that to some of those dusty old bones, being able to get things like collagen and protein out of some of these 200 plus million year old fossils, and then apply them by comparing them to modern examples of modern organisms, we can really turn these organisms from dusty old bones into real active places. So today, paleontology is really more about paleobiology. It's the biology of the organisms, how they lived, and we can really begin to recreate them. So the Jurassic Park film is great, but it's actually underpinned by a lot of science. And so now we've got a really deep understanding of not just dinosaurs, but a lot of the fossils that existed. And the kind of quality of information we get is kind of illustrated in the next slide. So these guys take bits of collagen out of these dinosaur bones. This is a 200 million year dinosaur bone. And they get this out, they understand through that the pigment of the skin, if they've got feathers, what colour the feathers would be like, how they walked, what strength their bones had, and things like that. It's applying modern medical science to those, and modern geochemistry to those. And this is a couple of examples of publications that have gone on in the last couple of months, okay? I pulled them off. The left-hand one is from an iguanodon. Iguanodon was about 150 million years ago. It was a dinosaur. It was one of those beak-shaped dinosaurs. And those of you who see pictures of dinosaurs which have got ones that look like they're reggae dancers with one thumb up in the air, that's an iguanodon. It's about 10 meters high, okay? It's got a really tiny brain. The brain sits up there on what is a very tiny skull, okay? But what they've been able to do now is they've been looking at in detail at iguanodon's brain in a couple of examples in museums, and they're actually now getting out details of brain tissue. So they're really deeply understanding how and what the nature of the brains were and how they worked in dinosaurs by taking our modern medical science, our modern biological science, and applying it back and being able to get this out. And most of the data is done, this is without intrusive, without breaking the fossil at all. It's just by serial sectioning, by visualization, by special visualization techniques using transmission electron microscopes and things like that. So we can do it without being disruptive as well. And the one on the right-hand side, I think is really neat. It was published in the last couple of months. And what they had there, they got a bit of fossil an early dinosaur. It's 200 million years old, a little one, and we got some of its poo, the coprolite. And then they serial visualized that poo, and they found it was full of bugs. And these are the beetles that were eating the poo after the dinosaur had done its business. So that's the kind of thing we're getting out now. It's making paleontology, the dusty study of bones, come alive by paleobiology. So that's what's going on now. And you get lots and lots of this. So all of these visualizations and animations you see are often really underpinned by some very fundamental and very radical science that's gone on over the last 10 or 15 years. And it's transformed this as a study. So stepping through that, what about geological time then? What do the fossils help us through geological time? And this is the image on the right-hand one is a story that starts down here at about 550 million years old, just above the Proterozoic. Remember I said after the Proterozoic, 550 million years old, you got the first animals with hard parts. So fossils start becoming very abundant from there on upwards. And you can see how we break down the geological column from 550 to today on the top into different stages and into different eras. So the first era is the Paleozoic. It comprises the Cambrian, Ordovician, Silurian, etc. The Mesozoic, Triassic up to Cretaceous. The Cenozoic from Paleocene up to Holocene. And then people talk about today as the Anthropocene, as man's influence over it. Okay? But what we find is that in the older rocks, right down here at the bottom, we get the primitive life forms that are largely extinct today, but we can look at them from the present is the key to the past view. And then during geological time, over that 450, 500 million years old, each set of fossiliferous strata, each set of strata containing fossils, contains particular sets of organisms that are distinctive for that time. And that they tend to become more evolved and more like modern organisms as you go with time. So strata of the same age can be identified by their characteristic fossils everywhere. So if we went down, this is the picture on the bottom left is Grand Canyon. If we looked at Grand Canyon rocks, Grand Canyon at the base starts somewhere down here below the Cambrian and takes you right the way pretty much up to the modern day in terms of rocks. And you look at organisms in there, and they're very similar to the same age organisms that we would see in the UK or in parts of Northwest Europe. Because there's similar kinds of sets of organisms form at different ages. So that's a way that we do relative dating of rocks. And we find, this was a picture I showed very early on in the first talk when they were talking about continental drift. What we find is that we can see groups of organisms in different parts of the world that you can only explain by having those continents brought back together before plate tectonics rip them apart. So we can see, examples. So this is Africa, South America, Australia, and Antarctica about 200 to 500 million years ago, when it was all part of one supercontinent. And we can prove that from the fossils, because we find different fossil groups that you can only explain. These different coloured bands are different fossil groups. You can only explain their presence if you put those continents back together again. It doesn't make sense if you didn't. Particular one, this bright green one, the bottom one here, called Glossopteris, it's just like modern Arctic-type ferns and Antarctic ferns. It only occurs in glacial environments. So it told us that when that occurred, there was a big glaciation going on over Antarctica, just as it is today, and the southern part of South America, and large parts of Australia, and bits of southern India, and bits of Africa. And we see this band of Glossopteris flora, around all of these. So it tells us that we can find the same kind of fossils that gives us the relative ages and helps us to understand how plate tectonics happened, which we're all experts on now. And then when we kind of look at the whole of geological time in that context, what we find is that going right the way back to 4.6 billion years old rocks, now we're getting the technology and the chemistry and the physics to be able to really analyze those. We're seeing some very, very, very simple bacteria back in those rocks now. Very simple, basic bacteria. It really wasn't until we get to about 2.5 billion years ago, and you're seeing this first complex cells in the center there, that we think that we began to get an atmosphere. So the bacteria dominated everything from there, this kind of primordial kind of organic soup. And once you get to about 2.5 billion years to 500 million years, then animals begin evolving very quickly. But there's still soft parts. The reason is because there's not enough oxygen in the atmosphere for them to secrete hard parts. It's only when we get to about 500 million years ago, into the Paleozoic, that we believe we've got enough oxygen in the atmosphere to allow you to secrete the hard parts. Okay? So all of this makes sense. Early, simple bacteria, more complex cells, evolving eventually into us at the end. Sorry for putting a Spice Girl there. It was part of the image. So the fossil record, a sequence from simple bacteria to more complicated, showing things have evolved in all of their ways with time. Now, what we've been talking about now to date is just about relative dating, because with the fossils we use give us relative dates. The way we can get absolute dating of the rocks is by looking at radioactive nuclides that are contained within rocks and using them to date the rocks. So we look at the decay of radioactive elements trapped in rocks at their formation, and how much they've decayed will give us an indication of how old they are. And with that, we can get an absolute date. So we can find fossils maybe in these rocks or nearby, and we can get an absolute date from them. They're mainly from rocks like these, volcanic rocks, igneous rocks, some metamorphic rocks, less easy in sedimentary rocks. Okay? But what we have now is the ability to take absolute dates. Here you use a variety of different radioactive isotopes. For young rocks, it's carbon-14 to carbon-12 decay. But for the really old rocks, you're looking at rubidium, strontium, and then into uranium, lead, as the kind of isotopic change. But by looking at the amount of those that are trapped in those rocks, we can give a real age date to them. And that's where we get the precise or the more accurate date for 4.6 billion years as the origin of the Earth. So our fossils help us to understand ancient environments. With the absolute dating combined with the relative dating, we can get a good feeling for how old the rocks are. So those are all the kind of powerful things, and the way that we're now using modern, biochemical techniques to understand the evolution and how these ancient organisms lived is a real transformation over the last 10 or 15 years. So when we look at geological time, there are a whole suite of catastrophes that happen, okay? Mass extinctions. So on the left-hand side of this image, you've got another table that shows you going from the Cambrian, the old rocks at 550 million years, right up to the present day. Each of those orange straight lines, and they come out of those orange lumps, each of those orange are points where there was significant and rapid extinctions of organisms. And by rapid, you're talking about over a very few million years. Okay? And there were some major ones. So there were 5 major ones. There was one here at the end of what's called the Ordovician at about 440 million years old. We think that's to do with the fact that there was a big ice sheet that covered probably the whole Earth, and it had an impact on the organisms at the time. It says here 40%, nearly 50% of marine invertebrates died at the time. There were no marine vertebrates in those days. Vertebrates hadn't really evolved. By the time we get into the Middle Devonian, there's another smaller extinction, but the really big one is this one at about 250 million years. It's called the Permo-Trias extinction. As we move from the Paleozoic to the Mesozoic, that's where it's defined, and nearly 90% of marine invertebrates died. Okay, there was a major change in the organic component of the world. All right. It says here 82%. They think it's nearer 90% now. And don't forget, marine invertebrates dominated everything, but a lot of the early amphibians died off at the time, and the dinosaurs took their place. So this was a big event, and it happened very quickly. We can tell that from dating of the rocks, and we can do it within, a few 5 or 10 million years old, 10 million years gap. There was another smaller one at the end of the Triassic, but the next big one was at the end of the Cretaceous, and that's the one that everybody gets excited by. That's when the dinosaurs appear to have disappeared very quickly. And we do know now that it happened probably over literally hundreds of thousands of years. We can get that level of detail and precision in our dating. So what are these causes? They happen very quickly. They weren't part of normal evolution. All right? You can't explain a late Ordovician extinction or the Permo-Trias extinction by dinosaur cataracts. I mean, people have kind of said that the dinosaurs disappeared because they all got cataracts, couldn't see anything and fell off cliffs. It's amazing what people believe. So it has to be something that's quick. Oceanic circulation changes. They tend to be a bit too slow. Rapid changes in sea level, again, they can happen, but relatively speaking, they're not going to be over the kind of short duration that we need. The thing that we look at today are lips. So I'm going to talk to you a bit about lips. Not these, but about large igneous provinces. And we'll come back to those in a second. So that's what I mean by lips. And also extraterrestrial impacts. There's no doubt that there is some correlation between some of the extinctions and those. All right? So what I'll do is I'll choose the two big ones, the two exciting ones. The Permo-Trias one, which is that one at 248 million years, right in the middle there, where so much disappeared at that time. About 87%, as I said, of marine organisms. Many of the vertebrates that had existed and evolved as the amphibians evolved, and the beginning of the dinosaurs kicked off after that. And then we'll talk about the Cretaceous-Tertiary boundary, which is the sexy one with the dinosaurs going. And then we'll look where next and when. Okay? So the causes of them first, before I kind of go and talk about the individual ones. In the last, I would say probably the last 10 or 15 years, it's become very clear to geologists that we get these periods, and it comes back to our plate tectonics. As these plates begin to rupture, the continental plates rupture, and you begin these forming these proto-oceans like the North Atlantic, then at that time you'll often get enormous igneous provinces formed on the continent around there. Okay? And when we get those, they are big features. They are extending over kind of parts of continents. They have enormous, it appears to have big molten magma changes in the continent, and they have very disruptive and very explosive eruptions associated with them. And one of the consequences also with the scale of these eruptions, they are big. We're talking about, 10, 15, 100 kilometre thickness piles of lava and everything else like that, extended over thousands of square kilometres in parts of the globe. When these happen, they happen pretty quickly, and when they start putting material up into the atmosphere, you get increases in carbon dioxide in there. If they happen to be going via coals and things like that, you get hydrogen sulfide gas. You get increased acidification of the oceans, and it happens relatively quickly. So lips, without any question, lips are one of the causes of mass extinctions. Not kissing, but lips. All right? So put that in mind. The other ones are to look at, possibilities of meteorite craters. So there's no doubt that at the 65 million year Cretaceous Tertiary boundary, the one where the dinosaurs disappeared, at about that time there was a massive meteorite impact in the Gulf of Mexico area, in southern Mexico. It's called the Chicxulub crater. I won't ask you to spell that. But it extends, you can see here, it's 200 miles across. We think that the meteorite that hit it was probably something in the region of 50 miles across. They've drilled wells into that old meteorite crater, into the Gulf of Mexico, and looked at the rocks. And the minerals that occur in there are all very distinctive minerals that are very characteristic of very hot, high temperature, sudden rapid collisions. And they also contain some indications of extraterrestrial mineralization as well. So we can see that. Here we've got where the impact crater was in the central image. That's where we think the impact crater is. here's a kind of a map of that part of Mexico that shows you its extent. And the bottom right is a gravity and magnetic image of what we can see. You see these series of concentric circles in there. And as I said, they've drilled wells into the shallow water there and down to about 1,000 feet. And they can find minerals in there that indicate that something happened very quickly. Picture up in the top left is an image of what it may have looked like. But it would have thrown catastrophic amounts of stuff up into the atmosphere when it happened. So it's probably one or both or a mixture of those two that it seems to be the cause of the extinctions. So kind of I've gone the wrong thing. So let's kind of have a look at that. Go to those mass extinction tables before. So on the left-hand side of that image, it's Paleozoic, Mesozoic, the different 8 rock types. Here's the Permo-Trias extinction in the middle here, PT, the 250 million year old one, and the KT one is the Cretaceous Tertiary one, which is the dinosaur one, about 65 million years. The picture on the right-hand side is were there any big, large igneous provinces, big volcanic events going on at that time? Well, there's no doubt there was at the Cretaceous Tertiary one, and we'll come back to that in a minute. But we also know we've got the big Chicxulub crater as well, the meteorite impact. The Permo-Trias less easy. There's some big, giant igneous provinces. Nobody until relatively recently has been able to find any evidence of a meteorite, but now they think they might have found some evidence of something down in Antarctica. So it may be that these sudden, rapid, catastrophic events are this combination of the lips and maybe something extraterrestrial, but they're not kind of naturally, you don't have to have them. The lips on its own is going to cause you a lot of problems. So let's take that a bit further. Let's look at the two. Let's look at first the Permo-Trias one. This is the 250 million years one, right? So here's an image of what the world looked like in that sense at that time. Estimated 95% of marine species went extinct then. Most of the early amphibians died out then, and the dinosaurs took their place. Plants changed in their characteristics. So it had a profound effect on the world. This is probably the biggest one. And what we find is that up in Siberia, in this area in Siberia, that's an image of part of northern Siberia, there was an enormous outpouring of lava. We call them the West Siberian traps. And we're talking about thousands of kilometers square of lava, and also thickness of something in excess of 10 kilometers thickness. So there was an enormous igneous province up there. And that also ties in time-wise with the early formation of the Central Atlantic, the opening of the Central Atlantic, where we know there's another large igneous province. So the Permo-Trias has 2 big igneous provinces that's going to be throwing out all sorts of stuff. The problem with the Siberian one is that the lavas were coming up and the molten magma was coming up and melting lots of oil and gas and coal accumulations. And that was generating, it must have been generating lots of hydrofluoric acid, hydrochloric acid, H2S and everything else like that was up in the atmosphere and would have literally killed everything off. It would have acidified the oceans as well at the same time. And now we're beginning to find the possibility that down here in Antarctica, or proto-Antarctica, because don't forget, at that time, all of these continents were together. They hadn't split. The early opening of the mid-Atlantic wasn't until about this time. So it was all one big supercontinent at the time. Down there, we think there's a hint that we might have had a meteorite crater as well. So we had this kind of perfect combination of events to happen. Okay? But the meteorite, I don't think, is an essential prerequisite. The scale of that volcanic activity, the large igneous provinces, is so big that it would have profoundly affected the whole world, and in a very short period of time. And this is a map down there in the bottom left. These are images of parts of eastern Canada, but this is a map of where that large central Atlantic lips magmatic province existed. So the orange areas are there where we can map it today. It was an enormous area to go with the one that was over in Siberia at the same time. So that's a reasonable explanation. It happened quickly. We know that. We can date the rocks very precisely. 2 giant lips. 2 giant lips hit the Earth, and potentially a meteorite as well, but we don't know for sure about the meteorite. So the next one is the Cretaceous Tertiary one, 65 million years ago. And this is the one everybody gets excited about because it's when the dinosaurs died and they suddenly all turned over and went, oh, I'm a dead dinosaur. It's not quite the same as that, but it did happen very quickly. And there's no doubt that around the same time we had this big meteorite impact in Mexico. The picture down there of Triceratops with a giant meteorite in the background is the postcard that you would have sent home to Mum at the time. All right. The other interesting thing that is at about the same age all around the world, we get a very distinctive thin unit of rock that has a much, much higher than normal background content of iridium. Now, iridium in Earth's rocks is a very, very small trace element, very small. Here, it's in enormous concentrations and in spherules, kind of glassy spherules. And it's distinctive and it's found all over the Earth. There's no question from this that this has come from something extraterrestrial and probably came from that big meteorite impact. So we have clear evidence that over a very short period of time, that meteorite impact had an impact on the rocks, and it probably had an impact on the organisms. So was there a lip at the same time? Well, yep, there was. In fact, there were 2 again. There's one down in India, in the Deccan Traps. Those of you who might have gone over to west side of India, and that's central western, you'll find these massive, great, thick lava piles, just like we've seen here, many tens of kilometres thickness and thousands of kilometres wide, and we call them the Deccan Traps. Here's an image in the bottom right of what they look like. So you've got a large igneous province down in the south of India. In addition to that, here we had the beginning of the opening of the North Atlantic. And there's no question that, again, this was another large igneous province. We were just opening the North Atlantic. You can see this is the opening, the map on there. And we're up here at this corner where Iceland sits. And you had enormous piles of lava in the Faroes. So if you went to the Faroes, you'd see these great thick piles of lava forming the fjords. We know what we've got here in Iceland. The whole of the Hebridean province in Scotland is all part of this overall large igneous province. So, 65 million years ago, meteorite hit the ground. We also had two big lips at the same time. Without doubt, those are the things that contributed and caused the demise of the dinosaurs. And I would argue they didn't disappear because birds continue to evolve, and birds really are more like evolution of the dinosaurs. And more we're seeing some of the late dinosaurs had feathers, very distinctive feathers that looked and behaved very similarly to many bird feathers as well. So, yes, big catastrophic extinction, and it happened very quickly, almost certainly tied to lips and the meteorite. It affected corals as well. Many of the coral organisms and things like that died out, and new forms formed very soon afterwards. And it formed the way over for mammals to kind of grow. So we've got, I think, what is a reasonably valid interpretation for these really giant mass extinction events. And the 2 big ones are the Permo-Trias and the Cretaceous Tertiary. So the question is, God, when's it going to happen again and where? Well, the only place in the world where you will find a large igneous province potentially forming today is Yellowstone. So those of you with real estate around there, no, it's not going to happen now. But my goodness, if there is a place where you would have a large igneous province in the world today, and of course these things can start and stop, but under Yellowstone you have an enormous hotspot coming up from the upper mantle, from a real hot convection current coming up. It's melting the crust, and you have a big, thick, magmatic pile of granitic, acidic magma just below the surface. It has formed the Yellowstone caldera. It has already exploded a couple of times in the not-too-recent past. So it has all of the possibilities of being the next large igneous province. So there's nowhere else in the world that has all of these characteristics that come together. So it's not going to happen next year. It's not going to be like the volcano in Jaime that suddenly on the 23rd of January, was it 1987, went boom, and you saw that great lava. But it's going to get it is the only place that's a candidate for a yellow for a ellipse in the future. It may change. It may end up being in Europe, but at the moment that's the best place. So I just thought, it's a bit different from the volcanoes, but it still ties into volcanoes. It still ties into Iceland. We look at fossils from different ways, and it's a different kind of thinking after you've had a week of looking at volcanic rocks and some of the most amazing geological scenery. We'll talk and look a bit about fossils. So thank you very much for all of your time. I'm more than happy to answer any questions.